Okay. So now yeah. So the topics will be like this one. Try to go a different sorting algorithms, and we try to compare the sorting algorithms by then. Okay. So why we need to sort data? Well, we know that we know we can do the search a bit faster. We can apply binary search, or in this case, we can find a the, let's say, the lowest price, the highest price in the very good way, the best way. Let's say if we have the sorted array. Now just a quick review on this complexities. So can you tell me if we have a sorted array? Now if we want to remove or to get the highest or lowest price of item in a given array, what will be the complexity? Let's say get the lowest price in an array of prices. What will be the complexity of that operation? No. In sorted array. In sorted array, it will be O1. No. Because you see because when we want to rate it, just to get the lowest value, we can just take the first item or the last item. It depends. But because it's sorted, we can take it. We do it in one step. Okay. Okay. So this is how. Here is same for different example, but the idea will be getting the lowest or highest price in the array. Okay. Yeah, it's sorted. We are working on a sorted array. Okay. So we can have better data structure because it is sorted. We can check better. We can do many things, and especially that will be the key application will be for searching. Okay, most of the time we sorted we sort the data because we want to search the data. Okay, now sorting is a time-consuming task. Okay, and we will look at the very quick one, sample one, and and later we may go through different sorting algorithms named cell sort, quick sort, heap sort. What you are saying, Minh? Sort data on unsorted array, there will be, and yeah, sure. Okay, we will see. Okay, now for sorting algorithms, of course, we know that it's very complex, and when we say it is complex or say it is slow, or but these sample sorting algorithms are easy to understand, and it have excellent performance in different situations. And some situation actually when the size of the data set is small, we can just use sample sorting algorithms without any problem. Okay, all of this will be O(n) square. Okay, that is the thing. All of these sorting algorithm will be O(n) square. Okay. Now, let's say if we have this one, if we have a sorting algorithms, we want to sort this one. Let's say last time I see that there's something that we can do together. Gallery. Okay. What is it? Okay. Okay. Sorry. So now imagine that you are in a class, or you have a list of items like this way. Now, if I ask you to sort the players here in increasing order of their height. So normally, what should we do? If we start from the very basic idea, what should we do in order to sort a list of students? What will be the way to do? So if I ask you to sort student in increasing the height, so what should we do? Hello. Hello. So if you are we want to sort this one, so can someone tell me the simplest idea, the way that you sort things in your daily activities, like sorting thing in like the money in your pocket, means that in increasing order, sort the bookshelf in increasing order of the height of the height of the book. So what should we do? So actually here we have two operations that we want to do. First of all, we want to compare, no? Because they have an order. We want to compare. The key thing is we need to compare one item here with respect to the others, and to do something. And second second operation we should do is we have to copy or swap or change the position of the items in the array. There are two basic operations that we want to try. So the idea is, so we try to compare two items. No, we want to swap or copy the other item in different places, and then the third thing, that one that we really want, is that we want to have a sorting algorithm that don't need any additional algorithms. Sorry, additional space. Because if we have, if we need some other spaces, that require problems in some situations. Say we have all students in one room, this almost full, and now if we need one another room with the same size to move everyone out and in again, so that will be problems. So we don't want to have some space on that. What though we don't want to use some extra space. Okay. So next, this is the idea. Okay, purpose sorts. Purpose sorting algorithms. If you have the bottle of your bottle of water at hand, when you turn the bottle upside down, you will see that normally they have bubble air that will moving up and down in the in your work in your in your bottle. So purpose sorts, the idea, basic idea is that I want to show you an example first here. If we have I don't know, if we have a if I can do in real class, we can have it. Sorry. What we do is let's say we have this one up first. So here we say we have the item A, Okay. So we have different items like that. Okay. Now, let's say we want to sort the item in the purple sort. The idea of the purple sort is like this one. So actually, what we want to sort in increasing order, ascending. Okay. So what we want to do is in purple sorts, the idea is we want to move the objects. Let's say this one, 100, to the right. Okay. The idea of the purple sort will be like this one. So that we compare this index, let's say this one and this one. Okay. They have two items. Let's say this and this. Okay. So we will compare 100 with this number. If 100 is bigger than this number, what we try to do is we try to swap it. Okay. And after we have that, we try to do the second thing. So we try to consider this one and compare with this number, this number 4 here. So we have 104. Okay. So 100 is still bigger than 4. What we do is we swap it again. So we have this. Okay. And then we have 115. Okay. It's here. Okay. So we see that we compare 115. We say that 15 is smaller. So what we try to do is we say the 15 and the 100 and so on. You see that when we do like that, the value 100 is moving from the first position here and moving to the right. Okay. And finally, if we do it in that way, so we try to say have like this. I will repeat it here so that we can see the value and we try to do. So next time what we do is we try to swap 32 here, 22 here, and then we have this value. I would 6 and 100 again. Then we have swap 1 here with 100. Okay, and last time will be 90 and 100. You see that the value 100 is moving from the first position to the last position. Okay, so that the way that we try to do in purple sort algorithms means that we try to compare the value to two items next to each other, and from the left to the right. If we are in the ascending order, if the left one is bigger than the right one, we swap the position of the two numbers. Okay, so that way after the first iteration, okay, what we have is we have one new array that after we do the whole loop from the first position to the last position, what we can say is that we have 30 here, we have 4 here, we have 15, we have 20, 22, we have 6, 29, and we have 90, and then we have 100. That is what we get by the end. Okay. Okay. So after the first iteration, the result. Okay. And then you see that clearly that 100 is here is okay, but the other is not finished in the final position. So what we should do next is say we do it again, starting from the left again, and we compare these two values. Okay, so that we have we do again 4 and then 30. Okay, after we have it, we do again 30 and 15, we swap it. Okay, and 23 and 30, swap it. And now in this step we have 30 and 59, so we keep it like that. Okay, then we continue. We have 1 and then 59. Okay, and then we have 59 and 90 is good, so we have 59 and 90 stay in the same position. Alright, and we reach the end. So that's it. So you see that in the second iteration we finish like this, and what we see, we have 90 here in the right position. Okay, and we continue for the next iteration. Let's write down again. So we have this one. Okay, so you see that is the idea. So we do it again and again. So you see that every time we finish one iteration from the first position to the last position, we have some number in the one number in the correct position. Though that is the idea. So they try to move the biggest or the smallest item in the right position. Okay, so that is the idea for purple socks. So purple socks. So the idea is compare first item, and then if we want larger, we swap it and move it to the next position. So that is the idea, and what we see is that at the end of the first iteration, what we have is the largest item is in the last position. Okay, so you see that back to our example. So if we have 5 or 10 or n numbers, so for each number we have to go from the first position to the last position, compare and swap if needed, and by the end of that iteration we have one number in the right position, the largest number in the rightmost position. So the idea that will lead to the complexity of the algorithms, because for one item we have to go through the whole array to compare and swap, and we have n items, so we have n multiplied by n, so we have n squared at the complexities of the algorithm for that reason. So because we have to go through the array, and for each iteration we just have one element in the right position only. Okay, so that is the purpose of algorithm. So what I really want you to do is I try to show you one example that have animation, and that may help you to see. Everyone, can you see the screen, the website? Okay, now I try to do, say, hey, the bubble socks, try to increase the size of the screen. Okay, in random, see that they do it in a quite opposite direction, but you see that let's do it again. So they move the smallest item to the top. You see, this is actually the real running of the algorithms. So nearly solved it. You see, so okay. So in the reverse order, we will do this. Okay, and this one. Okay, so that is the idea for the sorting algorithms, and here I will show you one example, and to see to give you one example, so that you can try to do it manually, just to make sense of the data. Okay, so again, so please try to do the sorting. I want you to sort here like this one. Let's say I have some number. Okay, so the index 6, 7. Say this. So everyone, please at home, at your desktop, please, or your if you have piece of paper with you, please try to do the bubble socks or on your own to feel the way that the algorithm run, and then we try to make some comment on the algorithms. Okay. So everyone, please try to take a piece of paper and a pen and do it. Hello everyone, can you finish it? Hello? Hello, hello. Are you there? Anyone here? Hello, hello. Okay, great. What? Okay. You are okay. Nhung. Okay, you try to implement it. Okay. Now, everyone, let back to this one. Take quite a long time. I cannot, because I cannot see you in person. I cannot. I don't know what are you doing and how are you finished the work. But now, everyone, please back to the slide and screen. Now, what we want to say about purple socks. Okay, so in the purple sock, there is one thing that is very important for when we analyze algorithms. We start from this one. So this is what we really want to say, is that after the first pass or first iteration of the purple sock algorithms, what we see is that what we have to do is we have to do n minus 1 comparison. Okay, do you agree on that? So we so for one iteration, we have to compare the first item with the next one, and then we move to the second pair, and then we continue to do that way. So we have to do n minus 1 comparison. And then the second work will be we have to do from n to n minus swaps depend on the data. Do you agree? And now tell me, when we have to do 0 swaps, when we have to do n minus swap. So when we need to do a 0 swap, is when we don't have to swap anything. When? Hello? Yes, 0 for one iteration means that actually the whole array, the entire array is already in sorted order. Yeah. And when we have to do n minus swap for one iteration. No, n minus 1 is not when the data in the reverse order. Yeah, reverse order is one of the situation. Yeah, I agree with that. But is there any other situation that we have to do n minus swap in the first pass? Let's say for the first iteration, we have to do n minus 1 swap. Yeah. For the first iteration, could be the largest number is in the first position. Okay, the whole array is not in the reverse order, but just the first item. Okay, for the second iteration, maybe we have to do n minus 2 swap, and the case is that when we have the second largest overall item in the second position, let's say. Okay, that is the operation. And then what we can tell about purple socks is that after the first iteration, what we know is that the largest item or numbers is in the last position or in the right position. No? After the one iteration, we know that the first item or the largest item will be in the right position. That is what we know from the first iteration. For the second iteration, we know is that the second largest number will be in the right position. Do you agree? Yeah. It means that actually is the way the properties that we must have in order to finish the sorting algorithms. Because what we say is that for every iteration, I will move one item to the correct position, the largest item to the correct position. So if we have an array of n elements, after n iteration, we will bring n elements to the right position, and the array will be sorted. Okay, so from the term of the complexities and algorithms analysis, where we say that it is the loop invariant. Okay, that is something that is unchanged. Loop invariant is a term say that the properties that we have after each iteration of an algorithm. Okay, is iteration in our for loop. So loop invariant in our case is that every time we will bring the largest item to the right position. Okay, and from the purpose of algorithm here, they say that because we know that, so for the next time we don't need to check for the last entry or item, because the last item in the array will be is in the right position already. So we don't need to compare with them with that number. We don't need to swap with that number. Okay. So that is the idea for the purpose of. Okay. Do you have any question on this? Okay. So otherwise, now let's have a look at the algorithms here. So what we say is that we have two loops. Okay. This from the textbook, we call it the outer loop and the inner loop. Okay, two loop. And what we do is we do the comparison if something, and then we swap. Okay, that is the thing. And now have a look at that. There's something that is quite special on this. Is this we call it a backward loop. It starts from the last element. Okay. Okay, and then we do it until we reach 1. The second thing is that we start from 0 in the inner loop. We start from this one to this one. The out is this. The out, this out is this number. Can you tell me what does it mean? What does it mean by this? Yeah, the outer loop is the limit. Yeah, for sure in the context. Yeah, the thing is that the out actually just tell us that they the last item that need to be solved at the beginning. Out will be the last element. This means we don't have anything. And after the first iteration, what we know is that the biggest value will be on the largest position on the right. Okay, so what we do here in the code is that out will be the index of the last element to be sorted. So after the first iteration, we decrease it by 1, means the rightmost element in the array is in the right position. So here, let's say we have an array, have something. So see, and the out is here. Okay. Okay. So for the first step, we have this, and we do the swapping. We compare, we swap, we compare, and we swap, and compare, and we swap, and compare, and we swap, and finally we reach the biggest item here. After we had the biggest item in the right position, so we move this one is to this one. No. So we don't need to consider this one. You are not displaying the screen, so what do you can you see the drawing in the slide? I'm drawing something. No. Yes, yeah. So there's something wrong with the machine of what of Minh, I think. Okay. So you see that the out will be like this one. So actually what we say, if for the second iteration we have the second largest number here in this slot, and it's okay, and we continue to go to the left. Okay, that is the algorithms. So the good version, let's say the exact implementation of the bubble sort. In you may learn many sorting algorithms or in sample code that we do the 2 for loop, like one of your friends submit. The first one is one goes from 0 to n, the second one from 0 to n, and we just compare and swap. Do you remember that kind of loop? So in basic course, you say you may have some for loop for something that yeah, in basic course serve, you say you know it on algorithms, and then you have the sorting, you say is let's say skip it. I'll make it uppercase, please. Let's say I just because this one and we have this. Sorry for the cases of the thing. Okay. The well-known code that students use most of the time when students try to do the sorting here. You do the swapping, like you have temp equals a I, and then you do some comparison. So whatever. So this is the idea that people try to, I don't know why, but compare and swap. This is one of the way that you can do in order to implement the bubble sort, but the correct version will be this on the screen. Okay, because we can eliminate just by few elements the number of items we have to consider. Okay, So from what we see in these algorithms, what we can say that we are moving the element, the biggest item, from the left to the right. Okay, and then we do one from here to here. Now I want you to play a bit with the sorting algorithms. Okay, now I want you to do the sort from the right to the left. I want you to do the sorting from the right to the left for an array of ascending order. Okay. Now, if I want to sort the item in the ascending order, increasing order of the value, but in these algorithms, what we see is that we do the swap and the compare from the left to the right. Okay, do you agree? And now, what I want you to do is to do in the right to the left. Compare here and move the item, the smallest item, to the first position. So please try to do it as a small quiz. Okay. So time to practice. The quiz will be like re-implement or implement the purpose of algorithms with left right to left
Yeah.
Okay, everyone, get a question? So you can do either and after that do take a 15-minute break. Okay, so I will set the deadline for it in like say half hour. Okay, so you can take do it in 15 minutes and take a break. Okay, and submit your solution to Blackboard. Okay, I will open it in Blackboard. No, yes. Yeah, means that you're starting from the largest index. Compare and swap from the largest index of the array to the smallest. Actioning, as the Queen mentioned. No. Okay. Let's have a 15-minute break. Okay. If you finish it, finish the implementation. So see you in 15 minutes. Okay. Hello, hello. Please, the others, please come back. And I need one volunteer, please. Show us the your code. So what we need to do? So we need to do is we start for the outer loop. No, we start from 0 to n elements, and we try to increase it one by one until we reach n element minus 2. No. And then for the inner loop, what we should do? For the inner loop, we try to do this comparison and swapping from the right to the left. Means that we start from n minus 1 and go back to out. And what we try to do the if it's bigger and smaller. We do swap instead of swapping from the left and the right. Now we swap. Just do the swapping. If the value is smaller, we swap. Okay. So đây the purple socks with the sorting from the right hand side to the left hand side. So I hope that you all can implement it. Okay. Do you have any question on this one? So everyone, so now let the homework. So here some other things to play with. So please try. Okay, we work with the left to right already. Maybe the hardest one. Then we have the descending order, and then we have the two forwarding loop. So your friend, yeah, thank you, Trường. You try to find, try to submit a code here. M is and Trường. So the others. So I have the one comment for you is one question for you is you have the outer loop is for n e I equal n minus 1 I less I bigger than 1 I plus plus. What is the meaning of this one? Can we do something like in I from 0 to I less than n minus 2 I plus plus? So my question is like, is there any problem if I change the code? Yeah, minus is my mistake, but for the second option and the first option, is there any different for your algorithm? The others, if you have an idea, any comments, please try to tell us. Just look at the code. The others. Here actually it's not good for the work of Trường because yeah, there's something that we really want to look at is this one, please. Here, what I am highlighting here is this one. In this one, we stop a bit sooner than 0. In the work of trường, no? You try to go from I minus 1 to 0 for both of the loop, or minus 1 or 1 or something. But in the correct, in the implementation, that we need to move to the, we need to stop a bit sooner. Okay. And what we have, your friends show us something here of Minh, you are showing us the code in Python, but at least what we can say that in the inner loop of the work of Minh, he tried to stop it a bit sooner. Say he stopped at I, okay. So that what we really want, we want to stop the checking just at the position that needed. We don't want to work with the sockets or the numbers that are in the right position. That is the things. Okay, that's it. So thank you everyone. So now we move to some comparison. So here, so when we say about bubble socks, okay, if you so when we say about bubble socks, we have said that the number of comparisons is exactly the same for every term. So we always have n minus 1 for the first iteration. We have n minus 2 for the second iteration, and we have one comparison for the last iteration. So if you do the loop without stopping a bit sooner, this will be n minus 1 for all of the components. No? The difference could be in this number, divided by 2 or not, somehow. Okay, so that is a bit of difference if you do the loop from 0 to n for both inner and outer loop. So if the inner loop you try to stop it sooner, so the number of comparison will decrease for the later iteration. And for the last iteration, we just have to do one comparison. That is what we want. Okay. So the size here is that now if we don't stop a bit sooner, the number of comparison will be n minus 1 multiplied by n minus 1 or n. Then we have this one if we have divided by 2 thanks to this optimization. Okay. So this is for comparison. Okay. Now for swapping, okay. So because we cannot know exactly the number of swapping we have to do this because it's strongly related to the data. Okay, so what we can say is just in the in general, it's mean we try to get the average. Somehow we have the swap occur half of the time, and what we can say is that the number of swap will be around n square divided by 4. That is number of swap. Okay, so that is the performance. And we see that where the worst case, so every comparison result in a swap. So the worst case will be the data in the inverse order. Okay, in that situation, so every comparison will result in a swap because we have to swap every time. Okay. So what we can say about bubble sort is that the swap and the compare operations are proportional to n square. Then the complexities of the bubble sort C O n square. Okay, it's rather slow. In big ocean, what we can say is that because when we analyze the code, because there's two nested loop, and in most of the case start from 0 to n, so we have n square. Okay. Now, what we want is that we have few small questions just to double check. So the bubble sort algorithms, what we can say is that the algorithms alternates between comparison and swapping, moving and copying, or copying and comparison, or copying. What would be the answer here? So the answer is A. So say what is the difference? Can you tell me what is the difference between swapping and copying? So when you implement the code, you will see that if you have to swap, we have to do somehow, in this case, remember, or normally we have to do 3 operations. No? Copy the value to the temporary data variable, then copy A to B, and then assign temporal to A. So we have 3 operations. And for copy, we just take the index, set the value to that position, and that's it. So in copy, we have 1 operation. In swapping, we have 3 operations. That is the difference. If we really want to analyze the code in detail, that will be the difference. Okay. And now back to this one, what we can say is that where is my mouse? Okay. Now, after you implement and you play a bit with the bubble sort, now can you tell me, do you see that is there anything that we can improve from the bubble sort algorithms? Actually, this question is the very first question that the data computer scientists, when we do the research, people have to always try to think about, like, hey, there's algorithms already, and now is there anything that we can improve? So in this case, for bubble sort, the very simple algorithms, do you think that is some problem that we can handle? We can improve in order to increase the performance of the algorithm in general. What can we do? So now, just one hint is that now what we say is that in the bubble sort, when we look at this one, what we can say is that, so in the bubble sort, we try to move an item from the first position to the last position. Okay, the way we do it, we try to compare and swap, compare and swap, compare and swap, and for the last position, last step of the iteration, we get 100 at the right position. So, and we have the notion of loop invariance. Is that the thing that we say, hey, I want to say we want to have, but the end is we want to bring the biggest value to the last position. No. So that is the thing. So what we really want, and what we want for each interaction in purple sock is that we want to bring the biggest value to the last position. So based on that idea, the one I really want to do is we try to find the element that should be placed in the last position. Okay, that is the idea for the next algorithm actually. So we can improve it by that way. So we have selection sort. The idea is now we want to do the selection. We try to select the max value and put it in the last position. So at the result, what we can have is this one. We can have a fewer swap with the same number of comparison. That is what we want. We want to improve the algorithms. Now, in terms of comparison, so for the complexity, you see that the number of swaps, we have it n square, and now we move it to n. Actually, when we just look at the number and the complexity, that is a big improvement. Do you agree? Because we see that n square is far bigger than n. So we don't want to do n square anymore. We move it to n. That is a very good improvement actually. So what we try to do is we try to reduce the swapping time. And one more remark is that comparison is actually an easy task. And if we can reduce the swapping time, is it more important than the comparison time? Okay? Because the swapping time always higher than the comparison time. So what the idea for selection sort? The selection sorts come from the idea that we just described. We try to scan all the elements and to select the smallest or the largest item, and after that we swap it with the last or the first element. Okay, and next we do the second time to find the second largest element to put it in the second position. Okay, that is the idea, and repeat until everything is sorted. So now have a look at the animation, just well, I know, just to show you to make sense of the thing. I just try to bring it here. Okay, selection sort. If you want to zoom it a bit, I can say that this one, play again. So see that we don't want to swap, we just go through all elements to find the best candidate and swap it to the right position. That's what we want. So we don't want to swap every time. Okay. That is the idea. Okay, so if we play the reserve order, so we don't have to swap every time we do number of swap. We just swap once per iteration if needed. Okay, so now there's the idea. Is it? So now have a look at this one. Okay. Now, selection sorts, the idea is again need to find the max or the min value in the array and put it in the last or the first position. That is what we want. So we, in one pass or one iteration, what we want is we want to have make one and the comparison, and but only one swap. Okay, for each. Okay. So here the code. Of course, it will be a bit longer, but the idea will be very different and very it is more efficient than the others. So we start from the outer loop for number of elements from 0 to n number of elements. That is the number iteration we have to do. For the min, we try to find the min value, the minimum of the array. So we start from out. So again, mark this one. We have out here. We start from out here and we do this. Okay. We start from in equal out plus 1 and we do in less than element. We try to find the min. If the min, we find the min, we store the index of the min and describe the position of out and min. That's it. So this part would be finding find the min and then swap it with the position. Okay, so the screen. And now I have one question for you. My question is, can we start here with 0? Just like in your proposal last time, your friend say he start from 0, and what we lose is that we may do some extra step. Is not needed, but at least it's still okay. In this case, can we start from in equals 0? Is there any problem? Can we do it? Everyone, please. The others, what do you think? Who say it's okay? Yeah, the answer is no. We cannot start like that. Just like Long telling us, easy like this one. Assume that we have an array. Okay. Let's say we start from this one. Is 8. It's not easy for me to write here. It's number 1. There is number 10. Okay. There is number 9. And let's say the number 3. Yeah. For the first iteration, of these algorithms, what we do, the idea, we try to find the minimum value in the array and put it in the first position. So our min is like this one. Okay, is 1. So what we have at the position after first operation, we have this. Okay. Okay. Đây first after the first iteration. Now, the idea here is that we try to find the mean, but this is very, very important, that our plus one, because now what they say is we try to find the mean from here, except the one. Number one is we skip it because it is the smallest value already. Okay, so we start to check from the second position to, this means on the remaining item of the array only. So the next mean will be this one. Okay, it's not number one, because here if you keep one here, and if we don't skip one, so the mean we find will be one all of the time, because it's the smallest. Okay, so the idea, they want very small but important point in this algorithm, on the implementation of these algorithms. Okay, so now I just want you to do the selection sorts again with this array. Now it should be very easy and fast with respect to the previous purpose sort algorithms. No, let's say what we have is here. So for the first iteration, what we have, we say mean is will be 1 at the index 5. So we swap 1 with the 0. So at the result we say swap index 0 and 5. Okay, so at the result we see we have is 1, 90, 93, 54, 52, and here 5, 2, and 4. Okay, for the second iteration, what the mean, because we cannot start from the first position here, because it's the smallest, it's there already. So we start from here, from here to the right. Okay, so the mean will be 3 at the index 2. So we scrap index 1 and 2. So that the result we have 1, 3, 90, 54, 52, 5, 20, and 4, and so on. So what we do next is 3, and the next smallest value will be 4, and swap 4 with 90. Okay, and 90. You see that in here in the selection sort, we do exactly what we want. We find this the smallest value and put it in dry position. So that is the thing. We don't want to swap many times. Okay, and so on. So everyone, is it clear for you? Do you have any question on this? Everyone, is it clear? Okay, the others. Okay, great. Thank you. Now, so we see that in any situation, we have the smaller number of swap, but we still have n square number of comparison. So the complexity of the algorithms is still on square, and we cannot have any improvement on the complexity. But for the performance on the running time, we may see it is better. Okay, so in comparison with the purple socks, so we have the same number of comparison is n square divided by 2. Okay, because we reduce the number of comparison every time by increasing the index of the inner loop. Okay, so we have the fewer number of swap. For bubble sock, we have n square divided by 4 in average. In here, in bubble sock, we have exactly n swap. Okay, it's faster than bubble sock for that reason. Okay, now the question. What will be the answer? For silicon socks, so what will be the answer? The correct answer option? Assume that we are talking about the algorithms that we see in the previous slides. Okay. So yeah, sorry, here there are algorithms we are working on. So the answer is, they go through one by one. For the largest key accumulated on the left, is it the key on the left? On the previous algorithm we saw in the screen, on the left we have the minimum value. Okay, it's not correct. Question D will be the same. Sorted item accumulate on the right. It's not the case because we start to put things on the left. The number of items shift must be shifted to insert each item, so we don't have any shifting. So the answer is B. But is it the correct one? Yeah, it B, because every time for every iteration we find the minimum value and we do it repeatedly. We try to find the new min for the remaining item every time. Okay, that's the answer. Okay, it's good, Long. Now a few more minutes. I try to show you this one. There is another idea from the sorting. Sorry, the last one we call it the insertion sort. So the idea is based on the insert an object an item into an increasing order array. There is one of the exercise I gave you. No? So now tell me, if we want to insert an item to a sorted array, what should we do? What should we do? Given a sorted array, now we want to insert a new item. What would be the general idea for insert an item into a sorted array? Yeah. You may miss, yeah, the idea like that, and we need one more step. Yeah, we have to shift, find the correct position, shift, and put the data in the correct position. Okay, that's good. Now, the insertion sort try to do the same thing, but now try to combine things together, to sort the data. This they say that let's say one of the best sample sorting algorithm, or the best of 3. This is the best of sorting algorithms among purpose sort, selection sort, and insertion sort. This is the best one. But still, all of them have the same complexities, O n squared. Okay. Again, they try to reduce the number of comparison and number of swap. They say it twice as fast as bubble sorts. Okay. Again, we could have algorithms with the same complexity, but the running time is a difference. In this case, it try 2 times faster. Faster than selection sort in some situation. Okay. Bit more complex than the others. They can use in many applications. But now, here's the idea. The idea for insertion sort is that they consider the whole array as 2 parts. The first part here, we call it partially sorted array. Okay, this part. And this one is unsorted. And what we want for each iteration is that we want to increase the size or the length of the partially sorted array. So every time we want to increase the size here, and if we increase it n time, the partially sorted array will be the array, and we finish the algorithms. We can terminate. So the idea is that starting from the array here, say we call it mark player or items. What we want to insert this guy into this sorted array, this sub-sorted array here. So what we should do? So we should compare now. First step, we say, hey, is it this one is bigger than this? No. Smaller than this? Yes. Move to the left of that guy. Compare this one. Am I bigger than this guy? No. Move to the left. This no. And this guy, maybe I'm a bit taller than this guy, so I stay here. So that is the right position in here. This is the idea. So what we can do is that we try to combine many things. So we try to make one empty slot by removing this guy from the array. By removing, actually it's not removing, but just I will try to store it in one temporary variables. Okay, and then in order to put it in the array here, I have to shift everyone to the left, to the right. No, in this case, so I compare the one in the temporary variables with this guy. If it's not bigger, I move it here. So that is, I will move one by one to the right until I find the right position and put it right place. Here, let's say I will try to show you in detail in a concrete example because it's not easy to show here. Okay, now let's say here I have my array. Okay, now what I say this is my marker. This is my marker. This at the beginning I have this guy 0 because he just have one element mean that it is sorted. Okay, what we want to do is we try to insert 90 into this array of one element. Okay, in this case, because 90 bigger than 5, we do nothing, so we move the item here to this position. Okay, so what we do in the second loop is that we try to insert 3 into the sorted array. So what we do, we say temp equal 3. So what we do is we have 5, 9, and we have number 3 here. And we compare 90 with 3 because 90 is bigger than 3. So 3 should be on the left side of 90. So we put it here, put 90 here. We copy 90 into the position here. Now I compare 5 with 3. 5 bigger than 3. I copy 5 into that position. So maybe I put it into 2 space, 2 rows, so that we can follow. And because I reached the beginning, the starting, the end of the array here, so I put 3 in the right position here. So you see that actually the algorithm we try to do in the same time the comparison and the shifting. Okay, so now what we have is this. At the result we have 52, 4. Now I repeat the task. So my marker, which I need to insert 52, 54 here, 34 here. So what we do again, I try to compare 54 with 90 because 90 is bigger than this one. I put it here. The result is that is. Okay. Now I try to compare 5 with 54 is bigger, means that 54 must be on the right side of 5, and so we copy here. So finally we have this and the result. Okay, and now my marker moves to this guy. So you see that we try to do the thing by just find the position in the same time we shift thing. So 90 is bigger than this one. I put it here. So yeah. So 50 is bigger. So we have here 5 is smaller than 32. So we put it here. Okay, that is what we have. So you see that on this way, what we see is that actually people try to do the shifting, but not really do the swapping, but just copy one by one on the way that we compare. And the thing is that we may stop a bit sooner. We don't need to go through the whole array in order to compare, to find the position. And one more thing is that we leverage the idea of increasing order of the partially sorted array here. So because they partially sorted, let's say especially in this case, this thing is a partially sorted array, so that what we can do is what we can say is that this one, we try to move this guy into the sorted array. So we go to the left until we have something here. That is, this guy is smaller than 32 because we know that in decreasing order that direction. So we don't need to compare anything else. And we know that here, everything on the right or the left hand side of this number is smaller than 32, and everything from the beginning to this moment is bigger than 32. So 32 it will be in this position. So you see that we leverage two things. We leverage the idea, the properties of the partially sorted array, and we can stop the comparison sooner. That is the key idea for insertion sort. You see that the idea will be insert into the partially sorted array. Okay. Is it clear for you, everyone? Do you have any question on this? Okay, otherwise I will try to show you. No question? Okay. Now what I try to show you, maybe the animation maybe is not in front here. Now actually what I really want to show you is I want you to do two things. Maybe I want you to do sorting first. Please try to do the sorting with one array like this one to let's say. Okay. For this array, please everyone, please do the sort, the insertion sort for this array. Okay, this one, and after that I will show you the code in the same time. I want you to play a bit with the real example first, and then see the code, CT, and then see the code. Okay. So please everyone do the insertion sort for this array, and if you finish with that, after you finish with that, read the code. Okay. So everyone, please do it. Let's spend like a few minutes to do the insertion manually to see what happened. So everyone, so like few minutes now, let's try to look at this one. It is for the insertion instruction sort. Okay, so we have the loop is start from 1 because we don't need to work with the first element. Out here is the one that helps us to mark the starting index of the element that we want to move in. So we try to put it in temporary data variables here, and now we do the while loop. Okay, if it's not reaching the beginning of the array, or the item is bigger, is still bigger than our item in the memory, so we do the copy here. Look at this one. It's not a swap, but it is a copy. Okay, so and then we reduce the index. After we finish the while loop, means that we reach the in equals 0, or we have in a at the in minus 1 is smaller than 10, so we stop, and then we assign the temp to that position. Okay, that is the insertion sorts. The idea is like we know. So the key things for insertion sort is this is very important to say that we see that the insertion sort can be faster because we may stop a bit sooner on the way that we go from the right to the left because they are sorted order. So we don't have to go to the beginning of the array every time. So that we reduce the number of comparison and we reduce the number of swapping and moving around in the array. That is the key thing. Okay. So now for the efficiency of the insertion sort, what we can say is that for the first iteration, we have to do one comparison. For the second iteration, we have 2 comparison at max, and for the last iteration could be maximum n minus 1. But the thing is that on average we have n, so the maximum will be n square divided by 2. It's just like the bubble sort, but on average it could be divided by 4 because we may stop at the middle of the array, as you may see in the way that you run the example. Okay, that is the thing. So that help us to have better performance for the algorithms. But again, we have the same complexities because in the worst case we have to do max number of comparison. Okay, for insertion sort we have a lot of copy but not swapping. Okay, and for random data, people do the experiment and we will do it in the lab. It tries at faster than bubble sorts, faster than insertion sorts, but again it's still on square for the running time, for the complexities. Okay, so that is the idea for the insertion sorts, and that is the few more slides to the end of our section. Okay, so for the data nearly sorted is very good. For data unsorted, that means nearly backward or in the reverse order, there is no faster than the bubble sort. It means because the number of comparison and the number of swapping is almost the same. Okay, as bubble sorts. That's what we see. The question we may skip it for next time. Okay, so a few more slides I will put it I will show you next time in class, in person. Okay, so I think that there is enough for today. So do you have any question, everyone? So otherwise, that's it. Thank you. See you next time in class. Okay. Looking forward to see you there. Okay. Bye bye.